Okay, today's lesson is about phase diagrams. And phase diagrams show the relationship between pressure and temperature. So we graph the pressure of a substance versus its temperature. And if you remember from the last lesson, we looked at a cooling and heating curve. And a cooling heating curve shows the relationship of just temperature versus something warming up or against time. So if we know the pressure that's being applied to something and its temperature, we can figure out what phase it's in with the phase diagram. So let's look at a general phase diagram, okay? And generally speaking, you have three lines. And in this section here, you have the gas phase. In this section here, you have the liquid phase. And in this section here, you have the gas phase. So what we're saying is that if you look at a combination of pressure and temperature, you can plot it on this graph and figure, whoops, sorry, I wrote the wrong word over there. This is, sorry, solid. Sorry about that. You can figure out what phase it's in. All right. Now, we're going to do this in atmospheres versus Kelvin because we're looking at problem number 26, which deals with hydrogen, and it has really low temperatures at which it boils and melts. Okay, one other thing about the phase diagram is these lines represent the equilibrium between the phases. So all of these temperatures and pressures represent, for instance, going this way, you're melting, and this way, you're freezing. So everything on the line is the melting freezing point. If you're looking at this line here, that is the equilibrium between liquid and gas, which represents going this way. We are vaporizing, and this way we are condensing. This line right here represents sublimation, solid going straight to a gas, and I forgot what this line is. A gas going, we don't talk about that one too much. Look it up. Gas going to a solid. All right. Now, this point is the equilibrium between a solid, liquid, and a gas, and that's called the critical point. And there are some rare times when you might see the critical point, and if we were in lab, I could show you a way to do it with a pipette and some dry ice. I've seen it in nature. I've seen a snowbank at just the right pressure and temperature where it's not just melting, but it's also vaporizing. And of course, the solid phase is there too. So that's kind of cool. So most people driving by a snowbank like that would go, whatever, it's got some smoke coming off of it or something. What's that? And they might not even notice that. But for me as a chemist, I recognize that as an example of the critical point. And I can't help thinking that way. That's just cool stuff. All right. Now, we also have an area here. Oh, man. I've got the wrong word there. That's the triple point. Excuse me. I need a little more coffee today. Over here is the critical point above which you would only have a gas, no matter what the temperature or pressure up there. Okay, so everything over here. Okay, all right. So for number 26, we've got the bones of what we need, but now let's do some labeling. We've got the melting point at 1 atmosphere. The melting point at let's just put 1 atmosphere like right over here. Okay, this is not going to be to scale. But the melting point is, remember when we go from a solid to a liquid. And that at 1 atmosphere, that's going to be 13.96. And, I don't know if the line goes exactly that angle or what, but that's good enough for what we're doing. The boiling point at that same pressure is a little bit lower, and that's a liquid going to a gas. That's pretty weird. So the boiling point is actually, no, the boiling point is 20.39. Okay. So at 1 atmosphere, let's put that over here. It's about 20.39. Okay, there we go. All right, we've got the important parts in there. We've got the triple point. That's at 0.07 and a little bit lower, 13.95 for the triple point. The critical point is over here at about, we're going to have to change our, let's put that up here. Let's say 13 atmospheres. So really, let's take that off, because I want to show you that not all curves are exactly the same. So this one is going to, at, let's say 33 Kelvin, and again, this isn't to scale, at 33 Kelvin, the critical point is going to be right there, okay? And yes, some of them do have straight lines, and some of them kind of curve around like that. Take a look at some of them in your book. And there are even some in problem 27 where you have a sulfur, a diagram for sulfur that has different shapes of the solid, like from a solid rhombic shape to a solid monoclinic state. And I seem to remember a test I took when I was getting my master's where we had to do some really difficult calculations on a phase diagram, and that thing drove me crazy, so I don't even like looking at it. So there you have it. Now you're going to be diagramming something very similar to this, a different temperatures, and it'll be a different substance. The main question from number 26 is, does hydrogen sublime at 0.05 atmospheres? Okay, so at okay, well that's down here, okay, 0.05. So yes, it's going to, let me do this in red. It's going to be at 0.05. Yes, it is going to, no matter, well, going up to at least 13 degrees Celsius, it's going to sublime. All right, I want to talk briefly about the phase diagram for water, and that is in your textbook on page 482. Okay, so you have for water, actually this line, I'm exaggerating it a little bit. Okay, so if pressure's over here and temperature's over here, and you've got your solid and your liquid and your gas here, okay, what that means is at a certain temperature, okay, at a certain temperature, as the, now listen carefully, this is wonky, this gets me every time. As you add pressure to an ice cube, for instance, it's going to turn into a liquid, okay? This is different from every other substance in the universe that we know of. So that's why when you go ice skating, okay, and you've got your little ice skates on, okay, people think that they're actually, they are melting the ice, but not really. What they're really doing is they're adding pressure on that little blade right underneath that ice skating blade or skis. You're adding pressure and you're causing the substance, water, to change from a solid to a liquid, okay? Yeah, it does melt, but scientifically, really what you're doing is a phase change and you're adding pressure. Now, this works very well until you get to a certain temperature, which somewhere around negative 30 Celsius, okay? Somewhere around negative 30 Celsius, you're going to not be able to add enough pressure to get your skate to add pressure to force the water to go through the phase change. Now, what does that mean? That means if you go ice skating when it's really, really, really cold, you won't be able to move. You'll just be on some solid. And the reason you move on the ice is there's a layer of water there, okay? The melted water that you have caused to melt. And if you don't have that, it's going to be very difficult to ski or to skate. And sometimes I've seen this when I've been skiing, but you can kind of take care of that with the right kind of wax on your skis, etc. So that helps. I think it's kind of interesting that at 30 degrees Celsius, instead of having about 4 layers of water molecules, in other words, liquid molecules, you only have 2 layers. And apparently that's not really enough to help you continue skating. So that's just some cool science, and I hope you understand phase diagrams. If not, send me a message so I can help you some more.